I am the exhaust. GB, Jabba, Jabba. Oh my god. Down your throat? Chat rate? GB, Jabba. You forgot to adjust your own weight. Is the class gonna happen, or...
Did you know Optimus Prime had only 12 minutes of screen time in Transformers 2007? Bumblebee had 21 minutes, and Megatron had 6. In Revenge of the Fallen, Bumblebee and Optimus had 11 minutes each, and Megatron was in third place, with 9 minutes. In Dark of the Moon, Optimus was first with 13 minutes of screen time, Bumblebee second with 10 minutes, and Sentinel was third with 9 minutes. In Age of Extinction, Optimus was first with...
Wait, I'm gonna get copyright strike.
Hello, Chris.
Yeah, hi.
Hi, sorry for the slight delay. How are you?
I'm fine.
Okay. So already holidays, I guess. School holidays?
Yeah, it just started.
Just started, huh? Okay, all right. Good. Okay, so we continue where we stopped last time. Let me just share the screen, which means we go through past papers. Still quite a few questions from the multiple choice, and then we will go into the structured questions as well. Most likely today already. So we've done a couple of questions, and actually, when I say multiple choice, as you can see, the paper one is a mix between multiple choice and then mostly actually structured questions. And we come to that, let me see, at some point. Yeah, later on. For the time being, it's also still multiple choice, but we know that doesn't make it easier in that regard. So let's go into that one. When you go into question 5, huh? And we've actually dealt with that. Not all of the questions may be applicable because we may not have dealt with all the topics yet. A lot, but not all. So this one is something we dealt recently, obviously. So we have alpha, beta, gamma. And of course, it's a very straightforward question, actually. And we have then one point to identify and say, okay, which three on the refer to the same kind of radiation? So let's just go on. So we have 3 diagrams, huh? To illustrate the mentioned behaviors. And we have then to figure out which of the labels on the diagrams refer to the same kind of radiation. Huh? So it's a multiple combination question, actually, if you want to say so. I think so. we have not necessarily looked into the magnetic and electric field behavior. So, would you have any idea, Chris? Which one is which?
For the electric field, I know that L is the beta particle because it has less mass and a negative charge, so it is more easily attracted to the positive charge.
Okay, good one. All right, good.
And M is gamma because it doesn't have charge, and N is alpha
Good
particle
one.
because it has a positive charge and is attracted to the negative part.
Okay. Yep. All right. Very good. So, and well, of course, it's pretty obvious, but nevertheless, when you talk about WXY, just to list it down makes life a bit easier. So, which one? What is W? Also alpha, beta, gamma.
Alpha particle.
Okay.
X is beta and Y is gamma.
Yeah, it's classic, right? That's hence the ABC actually. That's where it started. Okay, good. And the third one, PQR. So the magnetic field is into the page, huh? So or before we go into that, Chris, I mean, there's various ways to deal with that, but we see already now, right? So we have, let's say, we have alpha, beta, gamma, and we have W, X, Y, and we had N, L, and M, huh? Correct?
Yeah.
Okay. So of course now we could start to play around. Say, okay, do we have XL? Yeah, of course. So it would be R. Do we have double L? Nope. So that's already out, right? Agree? Because it has to be the same, right? So if it would be alpha, it would have to be WN and whatever in the third diagram alpha is. But we have only WLR and WLP. Again, the W is always linked with the N. So that doesn't seem to be the case. Let's see. So what about A and D? Maybe I'm wrong, maybe I'm right, but just it's one way to solve the problem before we go into 3. So beta would be XL, and in order to be correct, it would have to be R. Is that the case? Or XL, that would be beta. Is that beta? Or the other option would be YMP. Of course, we have gamma. Gamma, that would be gamma in that case. I have to write it a bit nicer. Gamma. So clearly the question is in which way it gets deflected from the electromagnetic field, which means there has to be the force, otherwise there's no deflection. And that applies to the certain law. Which one is that, Chris? Which law are we looking at in diagram 3?
Fleming's left-hand rule.
Yeah, exactly. Or
I
the
forgot what
Lorentz,
the
right?
directions are.
Say again?
I forgot the directions. What they
Okay,
represent.
no problem. So that's I mean, because yeah, there's always two ways to look at it. And if you take the Let me see. No, it's not so nicely shown here in this one actually. So when you left hand, yes, you can do, but usually we use the right hand rule. Remember? I mean, you can do it both ways actually. It's just a matter of what is what then, right? But typically we call it the Fleming's right hand rule. And the direction of a current caused by the induced EMF. So of course that's why usually we can use as well the left-hand rule in order to get the force, right? So, but it's actually nothing else but just as the application of the right-hand rule, as long as we know what is what. And do you remember what is what in terms of directions?
Index finger is current.
Okay.
And then I forgot which the other two. The other two are the direction of magnetic field and the direction of force.
Right. Huh? So I mean exactly. What are those now? 4 times 7. Usually easier. Okay, when I said right hand rule, yes, I mean okay, it's basically the same. We well, it's some think it's easier, some think it's getting more complicated, huh? With the left and the right hand rule, because when we talk about induction, we talk about the right hand rule, or if we talk about the motor effect, meaning the force, then we talk about the left hand rule. So that was a correct statement from you. Of course, you can apply either way, one of them, as long as you know what is what. It's just a bit different application. The key issue is, like you said, the index finger is the magnetic field in any case. Huh? So the magnetic field goes into the page. So it's quite usually the best if you use a tabletop and then say, okay, the tabletop is my plane. So obviously the index finger goes down towards the ground, the floor. So that's the magnetic field. And now what we see is then the force effect. Huh? So because we don't have to, the current of course is then the particle eventually. But right now when we say look at the force with the left hand rule, then the force is the thumb. Huh? And you see the direction of the particle. So when you take the middle finger and you see the force deflecting, so in which say, well, the particles move from left to right, the magnetic field goes into the ground. So in which direction does your thumb show now?
Left.
To the left, huh? Also away from you. Hm? Genau, left to the left in terms of the direction, yeah? Or when you look at it from the front of you, exactly. So which one is therefore P or R correct? Chris? When you say to the force is going to the left, so is therefore P being deflected properly or R? Just think, just use the tabletop and say, okay, my index finger is pointing to the floor. My middle finger points to the right along the tabletop because that's the direction of the particle. And henceforth, the thumb looks away from me, right? Not towards me, away from me. So which means, or in other words, kind of, this is your thumb, the index finger is going down. So you see the back, so to speak, and the middle finger shows this way. So, so which one, in which way does the force act now?
Up.
Up, or in that case, yeah, up. You may say up or to the front, also away from you, right? So Hainsworth, it depends on what we look at it. Is it from the top? But it says magnetic field into the base. So basically, our viewpoint is from the top. It could be as well from the side, of course, but to make matters easy, it's easier to think about from the top. So Hainsworth, therefore the thumb, therefore it goes this way, the force, right? Would you agree?
Yeah.
Okay. So Hainsworth, we are talking about can we say anything about the particle?
I think it depends on the charge.
Okay. So is the okay. So how to solve now that problem?
Um, I think it should be the middle finger is pointing upwards because uh, because the force is going the force is going from left to right, then
Mm-hmm.
wait, is the left hand rule for the induced one
There's one.
or
There's one. It's the right hand rule. There's one tricky thing which is always kind of complicating matters because the left hand rule goes with the current, which means the traditional or the conventional current. Hmm?
yeah. So the left hand one is um, converting current to force.
Exactly. But we have to be careful when we talk about on a particle level. This is when we talk about the current in the, let's say, the current through a copper wire and we have some induction effects, stuff like that. Then of course we always have to keep in mind, okay, if somebody gives me the current flow, I can utilize one-on-one the left-hand rule. But if I'm talking on particle level, then I have to keep in mind that, of course, like you started to say, that the middle finger is actually the opposite direction of the middle finger is the direction of the particle. So that makes life a bit complicated. Or twisting the left hand because because it's the particle has the opposite direction. So you have to actually go and twist your left hand, so to speak, and say, okay, as the particle is going from left to right, which means in the current flow is actually going from right to left. So I have to twist my hand. The index finger is still pointing to the floor, but my current finger is actually pointing to the left, and hence the thumb is showing towards me. Huh? So this is something we have to keep in mind, that at the time when these rules were brought up, let's put it like that, it was still at the time when the current was thought to be the flow of positives, of a positron or whatever. It was just plus charge. That was the typical name at that time. It was not yet known that there's an atomic structure which includes the electron, and actually the electron is the one flowing, but which is exactly in the opposite direction than what was considered for the what we now call the conventional current direction. But it survived. That leads always to some, ultimately unnecessary complications, but actually that's the reality, so we can't change it. And we just have to keep in mind, do I talk about the current? Okay, then standard rule apply for the left-hand rule. But that is typically what you would have in a motor, right? That you say, okay, I have the current flowing in this direction, hence in which direction is the force acting? That's important for a motor, of course. But when you go to particle level, we have to remember that this is not the current anymore, but we have to point the finger in the opposite direction because we talk about the particle. And henceforth, then we would be on this side, huh? And we would have this effect. So meaning we have the steel into the ground. The current actually is going in this way because it's the opposite of the particle flow, and henceforth we have this one, huh? Oh, this is then the force. So of course we can utilize the right-hand rule as well. We just have to be a bit sure. If you would apply the right-hand rule, but you would have to modify too much in terms of thinking. So that's why it's not a good idea. Better to separate and say, do we talk about induced or motor? Also force. Motor means force. Huh? Okay. So that would be R in that context. And which one would that be now?
A.
A, huh? Exactly. So that because the behavior of the A, alpha, beta, gamma in a magnetic field is a bit difficult to predict on our level. So that's why if you apply the Fleming's left-hand rule, we at least get the force, and then from combination we get it, huh? Okay. And now we go into the decay. Okay, lithium emitting beta particle. And we have A, B, okay, we have it here. So we have the A, B, C, D here. So obviously we look at the number of neutrons and the number of protons. So we have 8, step lithium, 3, 8. So beta emission means what? Beta means.
So it emits a beta particle, so a neutron becomes a proton. So there's
Okay, yep.
4 proton and 4 neutron.
Okay, huh? Okay, so we increase. So the number of protons go to 4, henceforth, 3 to 4. So we must be on this one. And what about the neutrons?
Increase 1, so no. Decrease 1, so 4.
how many neutrons did we have before?
5.
5, okay. Just a second, yeah. Just a sec. I mean, you're. Okay. Yep. Okay. So, no, that's good. So in Hainsworth, what is it now again, Chris? Just sorry to ask again.
D.
D, huh? Okay. All right. Okay. Let's see. Because I think, let me just flip through because I really would like to move on. No, that is all. Okay. All right. Nope. Then let me just go into the overview. Okay. Now I see. All right. Okay. So now we are back. Sorry. Now we are back into actually that was just still some questions from the atomic paper. Now I would like to go really into the test paper again, huh? So that's why I had to briefly check. So we did 9, 10, no, it's not such a good question. Okay, 11, so now we are back on the paper 1, huh? Okay. So we move away because we have done enough from that one particular, and I think it's more helpful to you now when we go into those questions again. Center of gravity, length of 10 meters, and the center of gravity is 4 meters away. So
4 times 100 times 9.81.
okay, yep. When you look at A, so you would say question answer A.
C.
C, exactly. Right. So which means 4 times 100 or times 1,000?
4 times 100 times 10 because 9.81.
Ah, okay, yeah, exactly. So I just heard. That's why I ask again. I just heard 4 times 10 100. So okay, yeah. C, all right. Yep. Not it's straightforward. Actually, just need to know what is a moment. There's not much more to know about it anyway. Okay. Now 12. Okay.
B.
B. Huh? Okay. Why not C? Why not D?
C is missing no resultant force, and
Mm-hmm. Yep.
D is only considering the resultant. It's only considering the force of the vertical axis.
Yes, right. Okay. In different words, exactly. Stating the basically it says it a bit in different words because here we have no resultant force. Here it makes basically what is the resultant force, right? But of course, it would be a bit too simple if it would be when there's only a resultant force, right? But it says it's in C because it only looks at the torque. But for quite a few, the torque is already something a bit old, huh? Okay, good. Well, I would not. Let's no 13 is too. Move on a bit because there are a lot of questions. Yeah, I would say 14. It's better.
B.
B, okay. Why?
Because the upthrust only depends on the volume of displacement.
Good one. Yeah, exactly right. It's a trick question, which quite often not quite often, but once in a while clearly comes up with the multiple choice questions, right? So that you have, as long as you have a very clear understanding of what's going on, you will not be deteriorated, right? Exactly. So upthrust. Oops, sorry. So here we are. So basically, the force upthrust is proportional to the volume. Huh? Okay. All right. Yeah, that's an interesting question. Mediums of different densities. Of course, we are looking into physics, so no chemical reaction. And now we want to know the density of the mixture.
Calculate the total volume by doing density divided by mass.
Yeah, right. Huh? Okay, yeah, we can skip that one too, and that results in actually in A. Huh? So we get 927. No. But the numbers are less important. Of course, ultimately it's the number which counts. Otherwise, you can't answer it. And the numbers are too close to make a qualified estimate, right? 927, 933, 957. Okay, is already a bit further away. You can say, well, obviously the 910 has a heavy impact, right? We're talking about nearly 7,000. Of course, they don't make life so easy to, let's say, end up on, say, 6,000. Then life becomes a bit easier. Like, say, this one would only be 500. Then, of course, you could easily make the proportions and get some qualified estimate. That is a bit more difficult. Okay, yep. All right, now, question 16. Oh, that's 35. I just jotted down. It's 35 joules, and at X it has 24 kinetic energy. Huh? Okay. Okay. Which makes, of course, kind of sense. And you have a change of potential energy of 16. Or delta.
So want to find the kinetic energy, the final kinetic energy gained. So it's 35 minus 24, and then 16 is the theoretical kinetic energy gained. So 16 minus 9 is 7. Wait. But, wait.
You're close.
Wait, 35 minus 24 is 11.
That's correct. The
16
difference in kinetic energy is 11.
Oh, and then 5.
So what is now 5 exactly? So what are you looking at its core? which rule or law actually do you apply?
Conservation of energy.
Yeah, exactly right. So the delta in energy that must be one goes into the other, right? So and this is not the case. So we are missing something, right? So we are missing 5. So delta E question mark what that is. And of course that is our exactly the friction force or the frictional energy actually. Or the work against the frictional force. So we can as well call it the frictional energy actually. Okay, yep. That's so conservation of energy, yeah. That's always a helpful approach. Sometimes the momentum, of course, but not here. Now we have a similar question, but applied to the efficiency. Or let's say we could as well say on the Planck, of course, right? There's a certain non-efficiency, but of course we usually rather call that the frictional force. Whereas now here in the motor, of course, something similar. There must be some friction going on, or whatever way, or loss of energy. Huh? So what is the efficiency of the motor?
C.
Okay, why?
Because Q over E is the percentage of energy wasted, and then
Okay,
1
yep.
minus that is the percentage of energy being used, that's useful.
Yes, exactly. Yeah, good one, right? Exactly. And important, it's very obvious not to fall into this trap, right? Which is of course something totally different, but it happens sometimes. The rest is pretty clear, huh? And certainly not this one. But sometimes in the heat of the action, some may forget that this is actually just the waste percentage, right? And not the efficiency already, because they may misread here that Q is the wasted energy and not the useful energy. Happens in a test. Okay, so we have different masses, horizontal surface, then raised to different height, of course, gaining gravitational potential energy. I actually, do you understand the question, Chris?
Yeah.
Okay, so how would you, what is the core of the question?
Uh, so the objects have equal gain of gravitational potential energy, but you can vary their mass.
Okay,
So I think it's A because potential energy is mass times gravitational field strength times height, and
okay.
meaning M and H are inversely proportional.
Okay, yeah, all right. Good one. So inversely proportional, right? So, and no, we don't have that. That would be a bit difficult. What if, I'll just say what if. So we have, okay, yeah, hey, it is. What if you would one would have been like that? Hmm? Why would it be this one and not that one? So why is one the correct one and why not two?
Because when you times, because 2 would be 2 would have a
Or could we even say that in the context if it would be one or two? Inverse, yes, I agree. Of course, that is completely correct. Both are inverse. Why? But would we know from that information, or what else would we need to know that we can say it's linear or non-linear, right? The first one is clearly non-linear. The second one is linear.
because I think I can prove it with like an example.
Mm-hmm.
For example, if I want to, if I want the result to be 20, then y can be 10, and I mean, if I want this
Ah,
result to
okay,
be,
yeah. Mm-hmm.
if I
Get it?
want the result to be 2, then y can be
Mm-hmm.
10, and x can be 0.2,
Mm-hmm.
and in the middle it can be, like closer to the middle it can be 4 and 5, and then towards the right it can be 0.2 and 10. So they have
Okay.
varying height, and it's not a straight line.
Okay, yeah, very good. Okay, interesting approach. Yeah, I like that. That is cool. Right. So when we think, when you think back to the law, the gravitational potential energy, um, what is the fundamental relationship? What is equal to what when we go with the alpha sign? Also instead of, sorry, not equal, proportional, I wanted to say. In the typical, when we leave aside the constants, we just focus on the core phenomena, and we talk about the gravitational potential energy. In other words, what is when we talk now, we used of course age, but what do we quite often use instead of height in the context of gravitational energy or fields? Sorry. Also, yeah, it's the same at the end, kind of, but of course only with the mass.
Delta H.
Yeah, I mean age we usually don't use, right? What type of objects are we typically talking about? And Hainsworth typically use a different placeholder. Of course, it's the same ultimately. It's a matter of perspective. But when you think back to the laws, do we usually say H or maybe use a different placeholder?
Like distance.
Yeah, could be distance, could be radius, exactly. Right. So quite often we use the R, the radius, because of the objects involved. But D is of course fine as well. And when we think about it, is the would you remember? I mean, because that's another way to say it. Is it behaving like this or behaving like that? When you have to, I mean, it's not the height, of course, but then of course it's like distance against the potential energy or the gravitational potential energy. How does it behave? The closer you come. So if you would go to the, let's say, from infinite, and let's say Earth as an object, for example, with a gravitational field, and when you would imagine that this Earth is, you can penetrate nearly to the core, just typical thought example, and would the resulting uh, increase massively or just be linear? Because you come closer and closer to the core, right? Um, it would be because it would be 1/r², right?
Uh,
That's what I want to drive at because of the gravitational laws, right? Respectively, when you apply that to the gravitational field strength and so on. That's why this one is then going towards. That's why we have that behavior. Of course, this is not. It's a bit. Well, here we talk about height and we talk about mass. So what I'm talking about is, of course, not one-on-one related. Your example is very good and to the point, but just it gives us an idea from that thinking that these gravitational field strengths are having a nonlinear behavior, and hence there's probably some reflection in the end in that when we apply it with different distance and mass combined, which we usually don't do, but there must be probably something in relationship as well. Huh? Okay, so total jump, we go into displacements. sorry, we can do, sorry, we can, well, no, we still can do 19 and 20, my bad, sorry. So we have Q. Q has half the length and twice the diameter. So this one has half the length and double, obviously. And both wires now, they could be like coils even, but we just call them wires here and there. So we put on the same mass, huh? Same mass.
Q is the twice of the diameter makes it 4 times less extension, and then the half length makes it half the extension. Then together it would be half. No, it would be no. Wait. Because twice diameter would make it have 4 times the area, and then 4 times the area makes it has 4 times less extension, and half length makes it 2 times less extension, so it's 1/8, and then 1/8 is 8/1.
Yeah, exactly. Oh, great. Yeah, very good. Very good. So, what did you have to do, Chris? Or what was the core to the answer? I mean, what you just did is clear. Just would like you to briefly say what was the core of the thinking?
Because if you double the cross-sectional area, and the weight is constant, it's equivalent of using 2 of the same wire.
Okay, good one. Yep. Well, just say mass instead of weight, not just. But of course, it's in the end the weight force. Just there you have to be a bit careful that you say either mass or weight force, just to make that distinction. Okay, yeah, exactly. That's a good point. And henceforth, then you can compare it like you did. Huh? Okay, very good. So it's obviously the geometry has an impact. Huh? That's the one of the messages, especially when you compare one to the other, like what we did here, right? So 8 to 1. So extension wise, it depends on therefore the purpose, right? So if you want to have a minimal extension, which one do you choose? That it's more solid, let's call it solid. Would you choose P or Q?
Q. Because it's more force to extend it more.
Exactly right. So that's why it depends. So it's not good or bad. Also, there's no such thing anyway, ultimately. But just to say, it really depends on the purpose what you're designing as a technical system, for example, right? Maybe you want something very flexible for whatever reason. It absorbs a lot of force. Then you, without giving it further, so you build in a spring ultimately, so it becomes a spring element. Then, of course, you choose the one which is reacting fast, so it absorbs it. Obviously, it goes into that deformation energy. Or you say, I want to have it very rigid, whatever. So it absorbs it into the structure, and hence you dimension the structure accordingly. Huh? Like a pillar, for example, that you say it shouldn't move, and hence you dimension it accordingly. Huh? So that's something we not to forget. What is ultimately the purpose, which of course here is not being discussed, but just as a side comment. Huh? Okay, 20 now, because it goes exactly into that plastic and elastic deformation. But in a different way than what we just discussed.
D.
D? Exactly. No? Ultimately straightforward. So the thing with such questions is sometimes it's very clear what the answer is. So best is then just to search for the right answer and disregard the rest. Well, the key is simple as what it is. One is reversible, the other one is not. Hence we talk about elastic and plastic. It's just words, but they have their meaning. And the rest you can just simply forget without even reading it, actually. In such a case, huh? Not always, but in such a case. All right, 21, we have a displacement variation. And we see time in nanoseconds, which makes an impact on the hertz, megahertz, or whatever, kilohertz. And we have millimeters, of course. Huh? But that is still the same, the amplitude. So which is it?
1/10 times 10 to the power -9.
Okay.
So it's 10 times, 1 times 10 to the power of 8. And then
Okay.
that would be A.
Yeah, exactly. Huh? Okay. The amplitude is a given anyway. That's yeah. Okay, yeah, that's good. Okay, so just have to put that into perspective, right? It's a bit more math than physics in that context, right? But of course, we need to know what are we talking about in terms of what is one what is one wavelength, so to speak. That's an indirect questions included, huh? So that we make the right cutoff. Okay. All right. Now number 22. So now we talk about the displacement of the air particle. Huh?
D.
D, okay. Why?
Because so nothing else changed it, but the intensity is halved. So if we change that to displacement, then displacement is divided by the square root of 2.
Okay.
Wait.
So we have.
Yeah, that's it.
Okay, so when we say the I mean, there's one. Yeah, it's a good point, Chris. I mean, it's absolutely correct, right? The frequency remains constant. So which one therefore will already be eliminated?
A and B.
A and B, right? Okay, so it's one of those where it's a bit more like Sherlock than anything else. And then, of course, we have to figure out, like you said, then obviously you have to say, okay, frequency the same, so it's about the displacement. Exactly. All right, good. Which statement is correct? So this is one of those which is, yeah, you really have to work. That's one of those examples where you really have to work through each statement on its own, right? And say, as it's not that obvious from outside, proceed under normal circumstances. And we can see that A, B, or just starting with A, there's a lot of cannot. Huh? That always makes life a bit more difficult instead of can somehow. And if you always think, okay, which one is really applicable, and Ainsworth is the cannot now, well, correct or not?
C.
C, right? Huh? Yep. Exactly. All right. Um, okay. Number 24. So which problem are we talking about here?
Doppler effect.
Doppler effect. Okay, that may be of help for the answer. Depends a bit on the or some is just basic physics that you say, oh, well, that can't be. But if, let's say Doppler helps. It gives basically when you think of the core of the Doppler statement, then I think you can figure it out quite comparatively straight.
D.
D, okay, yep, and why?
Because the wavelength is shortened.
Yes, right. And also the Doppler has a lot to do with the wavelength, right? Shortened or lengthened, that's basically the core in the first attempt. Hence, when we focus on that one, we don't have to do care about the rest, huh? So to speak, is there any statement about the wavelength? Okay, A, B, C, no, D, yep. Is it correct? If that's correct, then we have the answer, huh? Okay. Now, electromagnetic wave statements.
A.
A, huh? Yep. That's rather straightforward, actually. Now we talk about a string and a stationary wave. They're 48 centimeters apart. And now the question is, what is the wavelength of the stationary wave? Which one is it, Chris?
48 divided by 1.5.
Yeah.
30. Wait.
Mm-hmm.
32.
Yeah. 32 exactly. Oh, that's one exact. So you can as well say, well, if I look at this one, I have 3 such sections. Let's just call it sections. And of course, we know this is halfway. But nevertheless, just so that means I have 3 of those, but after 2 is a complete. So I can as well say 2/3, which is the same as divided by 1.5. Huh? Okay, that was quite straightforward actually. Now we talk about a semi-closed. What happens then to a wave? And now it's actually an interesting question. When would we not get a stationary wave? When we have the loudspeaker pushing in sound, so to speak. Or in other words, what is the condition that we have a stationary wave? Then of course the opposite of that is the answer.
I think we just find the number of waves here in the.
Yeah, that's okay. Yeah, that's one way to do. We can do.
And if we need a number that has 0.5.
Okay.
Because wait, no, wait, let me think.
Yeah, it's moving in the direction. Yep, you can think.
0.25 or 0.75.
Yep, exactly. So remember we had that. We have that when we talk about the order of the wave, right? For the one fixed at 2 points and the one at one point. Then we can and the relation to the frequency, right? With the first, second, and so on. Do we remember for the situation of a half open or half closed pipe, like here, what are the harmonics we can have? Or in other words, compared to the say with 2 fixed points. I remember, let me just put it like that. So when we talk about the either 2 fixed points or half open pipe, and then we can talk about in the, let's say, fixed, 2 fixed, and semi-open, which means 1, semi-open. And then we have the first, second, third, fourth, fifth harmonic, the harmonic, right? So in the position, like 2 string, right? That's the 2 fixed positions. Can we have all harmonics? So 1, 2, 3, 4, 5, etc.
What is a harmonic?
Okay. Remember when we okay, that's fine. So when we take the fundamental one, so this is here. Well, we don't really need the line, but this is this one, right? This is what we call the first harmonic. So what is the wavelength? This, of course, is L. Then what is the wavelength?
0.5.
Say again, sorry?
0.5.
Is it?
Yeah.
0.5 L for the, or I know you're in the right track, but just what do
L
we see here
is
between,
uh,
what do we see here? And what is the wavelength then? I know what you
the
mean.
wavelength is 2L.
You're right with what you say, but not related to my question. The wavelength,
Wavelength
just the
is
wavelength
2L.
compared to the length of the string, 2L exactly. Exactly. I know what you meant. What is the length is half the wavelength, of course. So 2L, huh? And this is what we call the zero frequency or the first harmonic. Huh? So that means when we have the first occurrence of a stationary wave, which happens compared to the length of that string, when the wavelength is then double L, so to speak. And when you have the second one, let's make it here, of course, second one is then like that. So what is then, let's make it like this, the red one. Sorry, it should have been red. And then the next one, so we talk about this one. What is the wavelength in the second case?
1.
Yeah, exactly. So 1L exactly. Huh? So that's the second. And when we go to the third one, then that is testing my drawing skills again. So we have should be like that. Huh? It's not really. So we have what is in that case the wavelength?
2 over 3L.
Yup, exactly. Yeah, and we have here the F3, and we call that the F, the second frequency. Sorry, that's not what I wanted to show. I wanted to show F0, 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 and henceforth, of course, we go by, that should be an F. We have 1, 1, 2, 3. Huh? So that's why we talk about the first, second, and third harmonic. Actually, it's related to the frequency, but typically, because when we talk about sound, we typically do not talk about wavelengths. We talk about the frequency, right? So, and that's why we call that harmonic. It's just a word, but it has obviously to do as well with what we as humans perceive as being harmonious in sound and not screechy. That we say, okay, when we get a stationary wave of first time round, then we have the base frequency or the first harmonic. If we then continue to generate a wave which just has exactly the same wavelength as the string, that's then the second harmonic. And then when we have the third one, of course, this is then 3 times the first harmonic, meaning the third harmonic. Huh? So depending on at what frequency or what the first harmonic occurs, what could be any, let's say maybe 330 hertz. Then of course the next one would be 660 and the third one would be 990 hertz. Huh? So if we now apply that to the same problem, but we don't fix it at the end, of course the waves look similar, but they are not fixated at the end. So there's no like that because it's open-ended, and they all come to the point here. Let me say like this. So in other words, we have a pipe, right? Goes like that. Not the best of drawings, but nevertheless, it goes like that. So similar principle, but we are not having a second one. That's not possible, right? Because in an open pipe, at the end of the pipe, it has to be, assuming now the pipe length has the same length as the string before, we can see that the first harmonic is a very different one. So the length of the air column actually is that the picture has to be like that. Then I can use the same picture actually. So my first harmonic in a pipe will happen. Of course, now I push it that back and say this is now length L, up to here. But I just want to use the same picture, so we forget about whatever happens afterwards. And in that regards, we have an open wave at the opening, and we have the drawing is not really useful in that context. Sorry, Chris. I will draw it once more. Okay, forget that. It's not really helpful for what I want to say. So we have it like this, and we leave that with L, and of course like that. So, or in other words, one typical observation is here, which I have not drawn so nicely in the case here, is that of course the wave is going to be, of course, always fixed as well. Huh? That's the core point here as well. So that this at the third one it needs here as well. But with the open pipe, or with the semi-open one, if you look at it like this, sorry, like that, then we have the first one like this, like this. At the second one, we have the same origin, but we have it like this. It's difficult to draw, my bad. So in other words, now it's better, you know what, we do it a bit differently, sorry. But of course, keep the pipe ending here, but imaginarily extend it here, then life gets a bit easier. So we start here, and have had the first one like that. So assuming this is the double the length. And then we have the second one. We don't have a second one, so I can jump that one. We have a third one, which is this one, because the second one is actually 4/3. So that's why we go to, sorry, the third one is 4/3. So we go actually into a picture where we have another one, which is 1.5. So the same we have here, going 2/3 and like that. Goes up, down, like this. It doesn't like that. So in other words, what we have in this case, we have the F0 still, of course, but the wavelength is only a quarter. So 1, 2 is not existing, but I still write it down. We have it actually at 4L instead of double L. So that means we only have here an open end again at 4/3 L, which means we have F0, 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 but this is not existing. So we go here into the third one, because there's no second one, because you will see that when you look at the wave behavior, it's closed or actually hitting the point here at the third one, the second one, so there's not existing, it has to be open, and so on. That's why, in other words, you only have 1, 3, 5, etc. If you go to this one, for the fifth harmonic, lambda 4, lambda 5 is then afterwards 4/5 L, and hence 5, 0. There's no this, and no this at F4. Huh? This was this one. So in other words, when you see a wave which has all the harmonics, also first harmonic, second harmonic, third harmonic, it's a string, meaning fixed at 2 points. The moment you deal with a semi-closed tube, you can have by definition, by going through the theory, you can only have the first, third, and fifth, and so on. Huh? So in other words, the odd numbers. And that's why when we look at that one, and we look at the possible outcomes, then we can say, well, which frequency of sound will not produce a stationary wave? So that means in this context that we cannot have 200 hertz, but we could have 100, or we could have 300, or we could have 500. Because of it has to jump by odds, not even. Do you see, you follow my logic, Chris?
To jump by 200.
Yeah, right. Because it only can be, also it says which frequency would not produce a stationary wave. So that means, could 100 produce a stationary wave? Yes. Could 300 produce a stationary wave? Yes. Could 500 produce a stationary wave? In that example, yes, of course, it could as well be, say, 300, 500, 700, or whatever. The key point is that with a stationary wave in a semi-closed, or in a pipe, also the wave is fixated at one point actually, here, that's where it hits all the time. So it's like a one-side fixed wave, ultimately stationary wave. Then it must be that at the various frequencies, you get a stationary wave, because that is then the respective harmonic of the result of the open pipe, or the semi-open pipe. In other words, yes, I can have 100, I can have 300, and I can have 500, but I cannot have 200, because it asks for one and one only. Of course, I can do the math as well, of course, and calculate it accordingly. That's another way to do it, with the length of the 85 centimeters. So when I look at the past one, so the first harmonic, that will always occur. But in a semi-closed pipe, the wavelength is 4 times. Huh? It's 4L. So in other words, here, for the first harmonic, it must be 4L. That means it's 3.4 meters, right? And the speed of sound is 340 meters. So what is the respective frequency?
Uh, 100.
Yes, exactly. 100 hertz, right? So then I see, okay, then I can already answer my question and say, well, if at 100 hertz it creates, which is in that context here, the wavelength is 4 times the length of the pipe, which is according to what I know from from a half-open pipe, or one-side fixed stationary wave, and it creates a first harmonic, which is at 100, then the next one can only be at 300. It cannot be, and at 500. Or in other words, it cannot be 200. Because when I look at the third one, at 3, of course, that is 4/3 of L, or 1/3 more. You can look at it like that as well. So that in consequence gives me the respective hertz frequency accordingly, and so on. Huh? It would be a different story if it would be a string fixed on 2 ends. Then of course the question would have to be posed differently as well, right? Because you could have any of those. It could be 100, 200, 300, 500 of course as well. So it would have to be, let's say, something like 550, for example, or whatever, in order to say, in the case of a stationary wave with a string, then it would have to be something in between which breaks the harmonics, so to speak. Huh? Because it's always an integer of the starting one. And if the starting one is at 100 hertz, the next one must be 200, then 300, and then 400, then 500. But with the semi-closed tube, there's always one missing in between, because according to what we can figure out, the wave is open at the not open at the wave is open for the harmonics in the semi-closed pipe, so it will never hit the point here, so you will not get this picture. Actually, that is something which you will not have in the pipe, but you will have that when you only have a string. Then of course you can have that pattern like we saw before. Is that okay, Chris?
Yeah.
Okay, all right. Okay. So it's always going with the difference between a string and a pipe, basically, and then accordingly with the harmonics you will have in the result. Okay, moving on to number 28. So we have the width of the gap is equal to the wavelength. They emerge accordingly, so we see that then the alpha continues, also the wavelength distance between the wave, obviously. So which changes occur? I talked already one too many. So the gap is slowly increased, So
And angle decreases.
Okay.
And the wavelength remains the same.
Okay. And why does the wavelength remain the same?
Because this is only diffraction.
Yes. Okay. All right. Good. Okay. Then okay, we talk about interference. Two narrow slits, so the two-slit problem. So if I want to increase the distance between the fringes, which one? It's a very practical problem actually as well, right? The very obvious one, kind of. So you want to see more better on the let's say on the screen, like here, that they are more distinctively apart. Let's say you make an experiment, you have the fringes, but they are a bit difficult to identify because you would want to measure actually ultimately, and it's a bit fuzzy, let's say. So what would you change in your experiment to get an easier measurable result for the distance of the fringes?
Increase the distance between the slits and the screen.
Yeah, exactly. It's quite practical. So that means if you are doing an experiment, of course you can influence the experiment with the laser you choose, with the wavelength, obviously. But that's not the case here. The frequency of the light, right? The brightness guaranteed not. The distance between the slits and the screen, absolutely. The distance between the two slits, nope. So this is then like, okay, there's a limit to how far you can go between the slit and the screen in order to make a proper measurement. But there's some distance you should keep in order to get a reliable result. We had an example last time, or the one before. It exactly showed that it becomes a bit difficult to measure, but okay. Now we have a diffraction grating. we have a lane, certain wavelengths of the light, and we have a semicircular screen. So how many bright spots do we see on the screen? And the grating is 2 times 10 to the power of minus 6.
So I set the theta is 90, and
Okay, yep.
so the separation times sine 90 equals n times the wavelength,
Okay,
and sine 90 is 1, so
okay, yep.
separation equals n times wavelength, so n equals separation over wavelength.
Okay,
So it's 2 times 10 to the power negative 6 over 5.4 times 10 to the power negative 7, and it would be 2 over 5.4 times 10. 20 over 5.4.
okay, so
So 3.7, so it should be 3 plus 3 plus 1, so it's 7.
okay, cool on. Okay, yep. Well, so that is step by step, yep, in order to get the result. Huh? All right, good. Yeah, it's a very typical question in its core, but the way it's being given is slightly different to what is sometimes the standard. Okay. We have number density of free electrons. We have a charge which moves through the wire. So what is the average displacement of these free electrons?
Uh,
How do we link that?
0.15 equals 0.42 times just so 0.15 is equal to cross-sectional area times
Mm-hmm.
number density times the electrons displacement,
Mm-hmm.
and the cross-sectional area is uh, 0.42 times 10 to the power negative 3 divided by 2, and then squared and times pi.
Yep.
And
Do you have it, Chris?
I cannot get the.
When you look at it, you
Oh wait, I forgot to divide by the elementary charge.
yeah, exactly. That's right. You have
Times
you
elementary charge.
so. Because you have 0.15 coulomb, right? So that means you have a certain amount of electrons which had to move. It doesn't matter in which amount of time because that will eliminate itself on both sides of the equation. And these 0.15 coulombs are actually, what is the charge of an electron, Chris?
1.6 times 10 to the power negative 19.
Yeah, exactly right. So if I want to have a charge of 1 coulomb, how many electrons do I need?
The 0.15 time divided by that.
Yeah, exactly. Or in other words, if I want to have 1 coulomb, I have exactly that amount, but of course as a plus. So I need 1.6 times 10 to the power of 19 in order to get 1 coulomb, right? Because each coulomb, each electron has that 1 over that as a charge. Huh? And now here we talk about 0.15, so we just multiply that with 0.15, huh? So or 15%. So we have something like 1.6 times 15%, that's 1/6, something like 0.25 roughly, or times 10 to the power of 19. That's how many we have. And now the question is, how many pass through that diameter? Like you said, you have the diameter, meaning we have the area, and now we have the number density of how many flow through. So, and it's of course per cubic meter. So the cubic meter is the time aspect, right? So to speak. We have the square meter. Now we just need to know how do we go to that number of what is flowing through, which is equal, obviously, to the one which generates that charge. Huh? That you had in your approach. So it's just that on the left, let's say if you equalize say, okay, the charge is equal to so many electrons. That's that part on the left hand side, and that has to be equal to, well, of course, to the number density times the volume. Volume, you have exactly the area. The missing one is obviously then the displacement. In order to get the volume, so to speak. And that is then exactly what we are looking for. So have you recalculated it, Chris?
It's 8 times 10 to the power negative 5.
Exactly. Yep. Good one. Right. So it plays a bit with our, I would say, kind of three-dimensional thinking, but put that into make a link between distance and time, so to speak, or in that case, then the height of the cylinder, if you want to say so, because the area moves forward, creates the virtual cylinder, which is the height, which is the distance, which on the other hand is the time during which the electrons flow. Huh? Okay. All right. Good. Of course, what I will do, Chris, I will send you that question paper because there's a couple of more. So you have that as a reference. And then next time we're going into not multiple choice, but we go into the structure questions, huh? So that would be the next one. That would be paper 2. And then we deal with these so-called structure questions, huh? Is that okay?
Yeah.
All right. Okay. So otherwise, just any time, tell me if you. Of course, now is holiday, so in tendency, you will not have new stuff to go through. So it's a good occasion anyway to go through past papers. And I think if done with the multiple choice questions, as we see, they're not. Some of them are more on the simple side, some are not. So you can still solve some of them by yourself and have a reference for future usage when you prepare for tests. And then we start with this one, huh? Okay, there's of course a not infinite number, but a high number of past tests we can always work through, which is a good, of course, a good preparation. You get the sense a bit of what type of questions are coming. You're very solid, so that's very good to see. So we deal with that next time. Huh? Okay, then I'll send that to you in the next 1-2 days through the center, and then see you next Friday. Huh? And yeah, okay. Happy Easter.
Yeah. Happy Easter.
Thank you. Bye, Chris.
Bye.
in one game. 1 turn. I believe in you, buddy.
Oh? Yo!
Why do I sound like that?
22 minutes. Bumblebee had 13, and Lockdown was third with 8 minutes. In Transformers: The Last Knight, Bumblebee had 12 minutes of screen time. Optimus had 11 and Cogman was third with 7 minutes. In Bumblebee movie, Bumblebee had 48 minutes of screen time and Optimus had 3. And in Rise of the Beasts, Optimus had 18 minutes and Bumblebee had 6. When you sum all that up, Optimus has around 94 minutes of screen time in 7 movies and Bumblebee has around 124. And the movies are 990 minutes long in total.
What? Bumblebee has more?
Keep going, I have to sit yet.
Go on. Oh, yeah. Come on, come on, come on, come on, come on, come on. Push, 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 push. I'm so sorry. It's okay. Right, bench press done. Well done to the ladies. Bryce knee.
Lawyer's reaction.
Yes, sir, please. Hey, stop right now.
I saw this really cute guy at the grocery store the other day, so naturally I followed him to the checkout counter, and when he gave the cashier his credit card, I peeped it to see what his name was. And then I Googled him and found his social media profiles, and I was able to tell that he was single. So I went through his friends list and I found his mother's page. And then I looked through his mother's page and I saw that she was a member of this book club that's in my area. So I sent a request to join the book club. So I went to the book club meeting and I met his mom there and we bonded over some books that we both liked. And she just thought I was so nice, and I brought it up randomly in conversation that I was single. And she let me know that she had a son that was single also that lived in the area, and maybe it would be cool for us to get together and chat sometime. So I gave her my number, which she gave to her son, and this morning he texted me and asked if I'd like to get together this weekend and do something. So I guess we're gonna go on a date. I'm really excited. I saw this really cute.
This is the biggest upset in boxing history. Joshua hurts Ruiz and starts going after him trying to finish the fight, but he gets overconfident and starts dropping his hands while in the pocket. So Joshua goes for an uppercut that Ruiz ducks under, and Joshua keeps his right hand down after throwing it. So Ruiz comes up top with a big left hook that wobbles Joshua and eventually puts him down. This is the biggest upset in boxing history. Joshua
I don't know what this is. This is from like 2017 or something. What am I so pressed about? I don't look, times were tough back then, okay?
Buddy, is this track and field, or is this something else? Triple G. Buddy, you, oh my god. Wait. Wait, classic aliens didn't shout? 别吵！